Hey, Michael.
What's going on, Rob?
Oh, same old, same old.
Yeah. I like your Rick. Pretty good.
That's trolling my chancellor. I put that on for all the meetings. He sent me a comment once about my Rick and Morty t-shirt, so I started buying Rick and Morty everything.
Cool.
I'm just kind of showing him that I'm tenured.
Yeah, right.
I have PDFs of the Goldstein and the Landau books, if anybody would like them.
Absolutely. I would love a copy.
I generally just send them out with the first email, but he had it set up so that I couldn't see whoever was emailed. So I figured I'd get the names and people who are interested. I have an old Goldstein, but I mean, I'm sure it's still fine, but depending on how much, I don't know how much it's changed. I know it's expensive right now. $170 is the cheapest I found it for the 3rd edition.
God dang. That is probably it probably has pages missing and
It's a brand new.
oh, brand new. Cool.
Yeah.
Yeah, it's still expensive.
About 212 is the average. So, did anybody hear from Luke?
No, I haven't heard from him. And I haven't seen Ken this semester either.
Hello, guys.
Good morning.
Hi, Dr. Sujesh.
Hi, Michael. Hi, Rob. And Aryan, I think.
Yes, hi. Aryan.
Hey. Are you new to Carbondale?
Yes.
Okay.
First semester.
Okay. So did you get a chance to settle down?
Yes.
Okay. I think we are more students, so hopefully we will see them log in. Michael and Rob, how was winter?
Not bad. I had a chance to relax for a little bit, but I was in need of it.
Yeah, me too. My winter break was okay. Dodging COVID everywhere
Oh my.
I went. Yeah, they got almost everyone I knew had COVID when I went back to Kansas. So I pretty much sat at home, didn't go to Christmas, didn't do anything on New Year's Eve, but it was nice.
Okay, good. And Aryan, are you from around here, or did you move in?
No, I'm from Iran. I just moved here last month.
Okay, good.
Welcome to the area.
Thank you.
Did you hear me talking about the PDFs of the 2 textbooks?
No.
I have copies of. Oh, there's Luke.
There's Luke.
I have copies of the Goldstein and the Landau book. If you would like me to send those to you.
PDF file or hard copy?
It's a PDF.
Oh.
It's what you could get off of Archive.
I think I have the PDF.
Okay.
Okay, thank you.
Luke, do you need copies of the text?
Yes, I do.
Luke, how was your winter?
It was good.
Right?
Yeah.
Good. And we have Abdullah. Hello.
Hello, everyone. This is Abdullah.
Hey, Abdullah.
Hey, Dula.
I'm good. Thank you.
Good. So are you, so we have 2 students who are fresh in SIU. One is Aryan and Abdullah. So
yeah.
Abdullah, are you around from this region?
I'm from Pakistan.
Okay, so
I just came. Yeah.
Oh, you just arrived.
Yeah.
Okay. Welcome. And did you
Thank
get a
you.
chance to settle down?
Yeah, I did. I came 1 month ago.
Oh, 1 month ago. Okay, so you get a good chance to do that. Okay, good.
Thank you.
You have 3 students here, like who are slightly more experienced than you, Rob, Luke, and Michael. So I think from what I've gathered, all 3 of them are can be very helpful. So I think I'm sure they'll be very friendly. So both of you, Aryan and Abdullah, you should mix up. It's hard to mix up these days with COVID around.
Yeah.
But you have some experienced people like Luke and Michael. I think they can at least be extra nice to help in this situation. Yeah. But Rob, you you also are from the COVID, so-called COVID batch, right? If you allow me to. Is that right, Rob? You're also
From the what now? The
you're also from so-called COVID batch. If I were to tell that, like I started a terminology that whoever got admitted during the pandemic, we can
Yes.
call it the COVID
Yeah.
batch. Not a good terminology, I suppose. Yeah.
I like it, but
You like,
Yeah, this is how we started our first semester, pretty much.
yeah. So, okay. So we are how many? 1, 2, 3. Yeah, I think, yeah, we are all of us here. We had Travis also registered. We are 6 of us registered. But I just got an email 5 minutes back from Travis saying that he has some scheduling conflict and he will have to drop this course. So we are going to be 5 of us. Hopefully it will be in a classroom. It won't be like this. I don't think any one of us prefers this over a classroom. So hopefully by next Tuesday it will be like that, but that's university has to decide that. It's not my decision at all. Rob, are you going to be in the classroom? Will it be possible for you?
Here or at my school?
No. I meant in this course you will be.
Oh, yes. I have the Tuesdays and Thursdays off so I can travel.
Okay. So you plan to do
Now,
that.
my school might end up going remote because we have a higher positivity rate.
I see.
And we hit 10%, and I'm going to be teaching Monday, Wednesday, Friday remote.
Okay.
I think SIU's is a lot lower than that.
Yeah, at least the email that we got today said some 2.6% or something. That's a 3%. Yeah, that seems. But that was only for about 5,000 people. So there's another 5,000 remaining. Yeah, I don't know. Yeah. So you think it will be open next week? That's your guess, correct?
I'm hoping.
Yeah, hope. Yeah, that's good. Okay. So this is, by the way, I'm teaching from home. This is not a classroom. So we'll see how it goes. Let me know, since you guys have seen some of the quality before, let me know if the quality is significantly bad. Yesterday I taught using this and those were undergraduates. They did say that, oh, I cannot even read. So I don't know whether they were really being extra critical or was it really bad. So feel free to point out. And I have some, at least yesterday, it was basically my wife had some flu-like symptoms. That was the main idea. I stayed, but both of us are negative according to tests. So I think I can always come down to the classroom and teach. Okay, so I should begin by, let me set this a little bit of Zoom. So for Abdullah and Aryan, I'm Shajish. And this is for all of you, Physics 510, Classical Mechanics. I think classical mechanics should be the first course all the graduate students should take, but 3 of you, I think Luke, Michael, and Rob, this is the last course you're taking. So you seem to be taking it in the reverse order. In a sense. But that's it. That's my opinion. All of you guys probably have taken classical mechanics in undergraduate level somewhere. So in that sense, it really doesn't matter. The ideas are going to be the same. It's probably going to be a little more detailed, and we will try to do it more rigorously. Maybe I'll try to do it just a little more rigor than that you see in the undergraduate level. So again, how is this? Is this readable? Better? Is it okay? Okay, as of now, it's it's all okay. So so first let me go over the syllabus. I think for 3 of you, again, Luke, Michael, and Rob, they have taken classes with me. It's going to be the same strategy, but I will go over the whole thing for Abdullah and Arun. So so let's see. Let me go to this site. If I can. Okay. So let's begin by, since this is online and you probably have a computer access next to you. So go ahead and go to this website. This is going to be our course webpage. So this is SPHYS.com, and there is TC, and continue on, but I'm going to write it this year 2022. That's a year 01, and then it is SIUC as the course number there. Is that readable? Okay, it is readable. Okay, good. So okay, I don't know what was happening yesterday then. Okay. Abdullah and Aryan, is it readable? Good. And can you access this right now?
Yeah.
If it's possible, okay. And in the first few sentences, you will see a syllabus link there. Go ahead and click on that, and you should see the syllabus. It should. Oh, camera is here. No, you guys cannot see that. Okay, just look at the syllabus. Okay. Okay. First part of the syllabus has my information on it. We typically will have, I will be available in the office. My office is 491. It is, have you guys been to the physics floor, Abdullah and Aryan?
Yes.
Yeah, so when you're entering into that region, it's a circular place, right? One of the first rooms is mine. If you're aware of the student lounge, it is right next to that. So typically I'm there. Feel free to drop by anytime, even to say hello. But office hours, surely I'm there. And I encourage you guys to use office hours as much as you can. And we'll go over that more. Classes will meet Tuesday and Thursday during this time, hopefully in room 410. Again, it's on the same floor as the physics office. Okay. The website I told you, I should also say that this is a private website in the sense I maintain this, which also means that there is a chance that it can just not work one of the days, right? Especially on the day you're having an exam. If that is down, you really can get affected by that. So what I suggest is that at least the important pieces, important means just the homework, that's all there is. Make sure you keep a copy of that on your computer. Homework is the only thing I can see. There is also going to be, these lectures are going to be recorded, and I will try to do that even during the normal, like even when we are having normal classroom lectures, I will try to get it recorded, primarily because I have heard from most of you guys, that's the only positive thing that came out of pandemic, is that the recordings apparently was useful. That was an overwhelming common theme I found among everyone. So I'll try to keep that, but again, I will try. It's not you cannot depend on that in the sense that you do not come to the classroom and say that, oh, I don't have it recorded. Whenever possible, I will do it. The technology has to support, the internet should be working, everything, a lot of things has to be working. But usually I've seen that it goes smoothly. So you can depend on it, but don't completely depend on it. That's the idea. It also means that if it is recorded, it means that it can be referred back to. So be careful in your presenting yourself. That's the best. But most of us are always. I didn't have any issues regarding that at all. Okay, so that's about lectures, and the recordings will be available on YouTube. It's going to be a private link in the sense that if someone searches for it, they won't be able to find it. But that doesn't mean that it is really private. If someone has a link, you can always access it. So be aware of that. If you have any concerns about that, meet me and then we can talk about that. Okay. Books. The best thing to go about is that I will not be following a book from first chapter to nth chapter. That's not the way I will be going. I will pick up concepts that I feel are relevant and which I feel in a certain order I will go over it. And there will be a few textbooks I will refer to. So here I list them in the syllabus. And the expectation is that you should go around, not only these textbooks, go around the whole internet and figure out what suits you best. I can help you with that, which textbook has better content as far as historically goes or based on the popularity between other students and other universities. But you will have to figure out what is best for you. And I can guide you as to certain books seems to be doing this better. But the expectation is that you find the resources and I guide you on that. Lecture notes does play a big role in this. What I've seen is that many students depend on the lecture notes. And the idea is that when you're doing the homework, you will really need the, I think you will really need the lecture notes, but make sure you can do your homework reasonably easily. I don't expect that you go back home and you open the homework and you can immediately finish the homework in half an hour or 1 hour. That's not what is expected. If you can, that's very good. Then you're in, then you have a very good background and probably you do not have to put in too many hours in this. But that's very rare. Most of the students have to spend a good bit of time on the homework. And even if you're familiar with the topics, just spending time on it, that's a place where you learn. Homework is the primary learning place for this course as far as I'm concerned. Lectures assist you with that, but mainly the homework is where you learn. That's why it's weighted about 40%. And I should say that in the homework, you can take help from anyone. To the extent that you can look into your friend's homework and exactly copy that down, okay? The only expectation I have is that you should write your own homework. Don't take a picture of someone else's homework and send it to me. I don't recommend that. Don't always do that, because if you are, or how about this? If you are used help, that means to say you have used your friend's help or the internet or me, you can even come to me for help. Keep a record of that. Keep a mental record of how much help you have taken, because when it comes to the exam, there will not be any help. You will be on your own. So if you could not do the homework and you had to take assistance, that means that you might struggle with the exam. So keep a mental record of how much help you're taking. Feel free to take help. You should take help, but keep a record of that and then do extra work. Like we are in masters now, you all know how to study. So figure out how to, and if you want help concerning that, come to me. I can advise you to a certain extent, but most of us have their own ways of studying. So I'll go by that. Is that clear? Again, homework, you can take as much help as you want. In fact, I encourage that you guys talk to each other. Discussion helps. Actually, all three of you, I think Luke, Michael, and Rob, they have even formed study groups, and they meet together on an online platform during the pandemic. So I encourage those things. I'm not involved in that. They do it on their own, but I will encourage that. And I think it is healthy and helpful for courses like this. Homework is not really a place where I assess, it's a place where you study on your own. And it, of course, I assess in the sense submission gives you points, but that's a place where you learn. That's my point. Exam is where I assess you, and I'll try to make it close to the homework, but and try to make it simple. But from experience, I know that what I think is simple is not necessarily what is simple for the students. So apparently it comes out hard. Again, talk to, I think Duke, Michael, and Rob are experienced. So I encourage you guys to talk about that. And it takes a little while to get used to the style of the teacher. Everyone teaches differently. And I do have some sort of style in that, the way kind of questions I ask. So probably it will help if you guys talk to each other. Okay. So that's about books and lectures and homework. And we'll have 2 midterm exams. I said there will be exams, so there will be 2 midterm exams and there will be a final exam. So almost every 5 to 6 weeks, we will have an exam. So 6th week, we have an exam. I think it's the 11th week, we have an exam, and the 16th week is the final exam. Yeah, so that's how we'll go. Each of them is, I think, no, midterm exams are 15% of each, and the final exam is 20%. So it's 50% exams, 40% homework. So there is a 10% remaining, and I'll talk about that in a minute. So just to give a breakup, so that is homework. So that's 40%, and we have midterm exams, 2 of them. So that's 15 plus 15, so that's 30 points. And then there is final exam. That's 20. So that makes it 90. So there's a 10% remaining. And what I will do is I will have what is called quizzes. And that will be about 10 points. Now, how does this quizzes work? Earlier, I have tried a situation where I give quizzes every lecture. That's not what I'm going to do this time, but it will be the same style in the sense that when I'm teaching, there is a chance that some discussion might come up. And I will mention during the lecture that this serves as a quiz. That means that you have to go and carry out that discussion yourself. It doesn't have to be with others. Go to the internet, find out about something. For example, I can ask, let's say, something about special relativity. It might even be possible that you're not heard the word at all. So you just go and find out what it is and spend a little time on it. I suggest that you spend only 10 minutes. Don't spend more than 10 minutes on it. But if you get interested, feel free to spend as much time as you want. But for the course, as a requirement for this points, don't spend more than 10 minutes on it. Usually can be even less. So especially if you're busy, just do the minimal, do whatever is needed, and read about the words, whatever I asked you to do a minimum and finish it off. But the hope is that you do spend a few hours at least once in 2 days or so for this course. And this motivates you to at least open the book and figure out what the homework is and so on. It's just a matter of discipline. And that's where the quizzes come in. It need not be there in every lecture again, but whenever I do that, then you have to submit that. And you write that out on half a page. Don't spend more than half a page, less than half a page, I would say. Make it brief. It is more for your curiosity. And you just have to prove to me that you really thought about it. Some of the questions can be really hard, so it may not be easy to, you might have just thought about it and you never really had anything to write about, like nothing concrete to really write about. Then you just say that, yeah, I did think about it. That's also a good enough answer. I thought about the question and that's it. But that you have to write that sentence, that's all. So it's a matter of discipline. Now, that's 10 points for sure, but there is more than that to it. So let's call this Y. So whatever points you get as a decimal, let's say it is Y, and this will be less than 1 and less than or equal to 1 and greater than or equal to 0. That means to say, for example, after the whole semester, you got 8 points out of 10. That means Y is equal to 0.8. Right, so it's a number. So how does this work? So this is an example. So let's say your score was 60 out of 100. Right. So at the end of the semester, I decide to return back some points. And the maximum points I can return back is 100 minus 60, 40 points I can return back. And what I do is I decide to give only a percentage of that, which I will call as A. For example, I can decide to return back 20% of the points. That's the decision I make at the end of the semester. I can decide to give nothing at all. So that's also possible. But how much ever I decide to give, if you need to get back that point, I will also multiply by that by Y. So that means to say that if you have full points in quizzes, then you're eligible to get all the points that I return back. But if you got 0 in quizzes, then you don't get anything. It's with why do I do this? From me, I mean, this shows the seriousness one is showing into the course. At least this much minimum, at least you have to open the website once in a while. So, and it has worked out fine. It is not the most popular thing that has happened, but it's one thing I do, and it seems like in the last few years, I have continued to do that. Not necessarily the best, most popular among the students. And again, if you have feedback on that, feel free to tell me about that. So Luke, Michael, and Rob, what did you think about this? Was this useful, or was it another baggage you have to carry on?
I've always found it useful because there are a lot of times there are things that when I delved into it, there have been some times that it's helped me on exams.
Okay, good. Okay, so Michael.
Yeah, I like it because, like Rob said, especially whenever we get into discussions that don't exactly line up with the course, and then we're given a quiz and we have to go research it. I've learned a lot that way and have gone a lot deeper into subjects that we wouldn't have otherwise talked about. So
okay,
I think it's good.
Okay, good. Luke?
Yeah, just the same as they're saying. But also if there's like a step in the derivation that there's a question about, I like that sometimes it saves time to just, oh, you guys can handle that, and like go on with class.
Okay. Okay, good. Yeah, that's good to know. Okay, so Abdullah and Aryan, you get a feel for what it is, right? Any questions on what this is like? Was that clear enough? Maybe it's not clear. That's a very complicated way of curving. So don't feel overwhelmed. This is the last thing you need to know about the course. That's some logistic part. There are sufficient concepts that you have to worry about. But you will get to know this. But this is the breakup. The only thing I will point out is that don't ignore the quizzes. Right? 3 weeks down the line, if you have already missed a lot of points, that's too late. So don't take the quizzes lightly. I'm not saying it's the most important thing, but at the same time, you don't want to miss on it later on that, oh, I missed on it. It's a very simple thing. Just submit something. That's the main thing. Even if it's just the question, just write down the question and submit it. That's good enough. Like
Got
it's about participation. Okay. And it is not going to be every lecture. There could be many lectures where it is not there. I think that was some issue I had, that managing this became a little difficult. So if it's not there, it's not there. If it is there, it is there. It might be once in 3 lectures, or it could be 5 times in 1 lecture, either way. Okay, so we'll see as it goes. Okay, so that's all I have for the syllabus and the logistics. Any questions, especially Abdullah and Aryan? Anything you can think
I
of?
actually didn't understand about the quizzes. Are they like we have to solve a problem or just a simple question?
It could be, one of the questions could be, which equation describe the universe? That could be a quiz question. Okay, give me one equation that describes the whole universe. No one knows probably. So it's an open-ended question. Sometimes, as Luke pointed out, I might be in a hurry and I'm doing a derivation, and I go from one step to the other, and I know that all of you guys can do it. So I say that this is a quiz. That means that you have to finish that. So that becomes a very concrete question. Right? So I could ask a very concrete question, complete this integral. Right? That's a concrete question. Another question could be, what is time? Right? What is space? What is time? That's a very philosophical question. There may not be a concrete answer, or maybe there is a concrete answer. I need not phrase it thinking it is a concrete question. So it could be an open-ended question. That's fine. Either way, even if it is a concrete question, I don't expect that you need to do it. You only need to participate in it. That's fine. If it's a vague question, surely no one can participate in it. You only have to think about it, right? And then you say that, yeah, if you have something concrete, if you feel like sharing, go ahead and do it. But often I've noticed that most of you guys, at least like Luke, Michael, and Rob are here, and most of the students get something to talk about. And even if it is going to the internet, that's okay. Right?
Okay,
I can, yeah. So did I answer your question?
Yes, yes. That's good.
Yeah.
Thank you.
And earlier I used to have it due online, and that surely brings in some organization to that, but that also means that I have to always open it and put a deadline on that and so on. So it's a good bit of I feel unnecessary work on me. So I'm going to deal with it using hand notes whenever it is there. If it is this lecture, it is due on the next lecture. So if I give a quiz today, it is due in the next lecture. If it is online by any chance, I hope it is not, then we will find a way to make it due on D2L. I hope it is not, and it is just easier. That way I just have to collect it and put it together. I think last semester I had a problem where Rob was submitting online and others were doing it by hand. And sometimes those things for me becomes a little trickier. One would think that it is the simplest thing, but it's just managing things. I get bad at that. But you will submit it in the classroom. That's what it is. Right at the beginning of the class, you just submit a sheet of paper with the answers to the question. Answers, if they exist, then you submit it. Is that clear enough?
Yes, thank you.
Well, and no delays for that because of the nature of the quiz. The whole purpose is that you're disciplined. So there is no, I mean, quiz is quiz, like it gets over on that. So don't expect me to track some delayed submissions and so on. But I have not had any serious issues with that, honestly. Okay. Any other questions? Okay, so let's do a little bit of what we can. Maybe I can ask you guys, what do you expect in a course on classical mechanics? What are the topics you think is related to classical mechanics? Chapters names are good enough if you can think of topic names.
I think for this course, it's mainly Lagrangian and Hamiltonian. Okay.
Yeah, good. Lagrangian. Yeah, let me list them. Lagrangian, Hamiltonian. Anything else?
Are we going to start with the coordinates, or we should know it already?
You mean the generalized coordinates? That's what you have in mind. Maybe, yeah, I don't know. Yeah, we'll see. Yeah, I think probably I may not spend a lot of time on generalized coordinate itself. I think you mean, yeah, I may not spend too much time on that, but it'll be clear as to how it can be generalized into more complicated coordinates. Yeah, good points. I think generalized coordinates, that's something that one thinks of. Anything else you can associate with classical mechanics?
The principle of least action.
Yeah, good. Yeah, so I think let's yeah, least I like to call it stationary action principle. Yeah, nice. Anything else? What are other things you remember from your classical mechanics in undergraduate, let's say?
Newtonian mechanics.
Which mechanics?
Newtonian.
Oh yeah, Newtonian mechanics. Sure, of course, you should begin with that, right? So yeah, so yeah. Think anything else you can think of?
Well, no, one topic that showed up. I said one topic that showed up when I was looking for copies of the textbooks. Perturbation.
Perturbation. Okay. Oh yeah, I think we will be able to do this. Yeah. Okay. I won't call it perturbation, but yeah, we will cover that. Yeah.
It tends to be the last chapter in most of the mechanics books.
Okay. Okay. Yeah, I think yeah, we will do this. I think especially it is nice to, for example, when a planet is going around sun, you would like to know how much it is getting perturbed by Jupiter, let's say. Right. So that's a good thing to, because three-body problems are hard to do, but at a perturbative level, it is reasonably easy to do, and it captures a good amount of for the accuracy with which we make observations. That's good enough because the effect is really small. Yeah, that's a good thing. I don't usually do it under the name perturbation, but that's good. Let's see. So what I will. What do you what would you like to be in classical mechanics in a course, in this course, let's say? Is there anything that you would like to be added for sure?
So I remember we did some Euler angles in mine, but I didn't really get it when we did it in my undergrad.
Okay. Let's see. Yeah, I will do rotations basically. Rotations. I can do, so I'll do rotations and Euler angles. I may not call it Euler angles, but we usually Euler angles are used to understand the rotation transformation. And I don't call it Euler angles at all, but I will do it in the infinitesimal context. So probably that is a direct connection. I'll see at that time. I will look into it whether I can. How about this? I will introduce Euler angles and probably in a half a lecture and then immediately go into what we need to do. So that should be possible. What else do you think you would like to have? It's a hard question to pose because you guys tell something and then I should be able to do it. Anything else you can think of? What I think from beyond what you guys have already listed, I will try to do Poisson brackets. On brackets. I feel it is relevant because this connects with quantum mechanics. Whatever we have in commutation relations, there is a one-to-one relation between Poisson brackets and that. So what I will try, I mean, hopefully I'll start with very little of Newtonian mechanics. That's just to point out that there are reasonably complicated problems that we do not see in an undergraduate introductory physics courses. So try to do some slightly what we don't come across there. I shouldn't say we do not. The courses that I teach at an introductory level, I do not cover those things. So I will try to do a couple of examples, basically 2 lectures or something, and then immediately go into, the idea is to go into Lagrangian and Hamiltonian, but for that, we have to reach stationary action principle. So let's say I'll start with this and go to stationary action principle. That is broadly coming under what is called variational calculus. Right, so it's often called calculus of variations. Right, that's what we will do. And I will, for that purpose, I will introduce the idea of what is called functional derivative. Right? So this is functional derivative. This turns out to be not a very popular way of doing it. Most textbooks do it in a slightly less rigorous way. This is a slightly more rigorous way of doing whatever, for example, Goldstein does. But the idea is just to introduce it, and afterwards, which method you use doesn't matter. So I'll try to motivate functional derivative. If you're having too much difficulties with it, feel free to use the standard textbook stuff, and that's fine. Eventually, the idea is to be able to do the functional derivative, or do a variational approach, not really which method you use. Once we do this, then we will go to Lagrangian and Hamiltonian. Lagrangian and Hamiltonian basically is a consequence of this variation calculus. The idea is that the whole of Newtonian mechanics can be thought of as a stationary action principle. Something is getting minimized, and we call it the action, which is basically written in terms of the Lagrangian. So that's an observation that people made in the first 100 or 150 years after Newton, that there is a lot of generality in this. It need not be that Newton's equation is fundamental. One can think of something this as a fundamental principle. And it has been very successful. We have been able to write many theories, or whatever we know it has been possible to write it as a stationary action principle, but it also has a lot of limitations. For example, friction, right? The way we understand friction at a very simplistic level in introductory physics course, we write μs times the normal force, right? Coefficient of friction times normal force. Those things are harder to capture in a Lagrangian physics. This part, maybe one can do a little extra work and actually get it. But once you come to dissipation, like heat, it's almost impossible to get it in on the Lagrangian mechanics. So there are a lot of limitations with Lagrangian mechanics. And I think that is the reason why you don't see Lagrangian mechanics being used so much in engineering departments, right? At a fundamental level for fundamental investigations, it's very useful. But at an applied level where there are empirical relations, it's not really the most useful thing. So we should know the limitations of that, but it's a powerful approach. It's nice to realize that Newtonian equations can be thought of as a much more general principle. It's almost like saying light, when we do reflection and refraction, we learn it as law of reflection and law of refraction, right? But it's also interesting that Fermat's principle says that light always takes the shortest path between 2 points. Right? That gives an additional feature to that, how does light know that which path to take, right? So those kind of questions comes in. But Fermat's principle exactly reproduces what our law of reflection and law of refraction is. And it's something like that Newtonian physics can be captured using stationary action principle, which is like Fermat's principle. It's a minimization principle. It tries to take the shortest. In this case, it's not the path. It tries to minimize the action. And within, I think, the second week or so, we will actually start with the example of Fermat's principle, where we'll derive that whatever we study as Snell's law, we'll try to derive that using the idea of this functional derivative and so on. So we'll try to motivate that. So the idea is we'll basically have variational calculus at the central level. We'll try to understand what that is and try to develop Lagrangian, Hamiltonian, and right away do Poisson brackets if possible in a continuous level. It's all ways of minimizing things. And then we will do specific examples. We will see that most of the real life examples, for example, even if you have a simple pendulum, already the pendulum becomes complicated, but if you want to solve exactly, you always have to make approximation. Most of the times, you have to make approximations to be able to solve it. Even the pendulum, right? Pendulum, you make the approximation that it's a small angle approximation, right? If you make the angle very large, it's not that you cannot solve it, you can solve it, but then you have a special function, which is called the elliptic integral, and you have to write your solutions in terms of elliptic integral. Not that it is not easy, it's just most of us do not have a very intuitive feel for all the functions. Like, for example, if it's a sine function and cosine function, we have a very good intuitive feel for it. But if I tell you this is an elliptic integral, that's a function like sine and cosine, but we may not have an intuitive feel for it. So due to that reasons, often we depend on a less rigorous way, but more intuitive for our purposes. So that's one thing we'll do, and we will start working on those problems, and we will see that that's where I will try to introduce perturbation, not in that language, but we will need to do approximations, and that's where we will do that. Then we will, one of the problems one can spend a little time on is a Kepler problem. Historically also, this was the most studied problem because once Newton gave us equations and there was Newton's law of gravitation, where do you apply it? You try to look up in the sky and you realize that you can predict where each of the planet is going to be to a pretty precise, to a very good accuracy, and you know exactly what is affecting this. And the only thing they couldn't predict is the small deviation that was seen, and that was called a perihelion of Mercury, or perihelion of, I think it's perihelion, check the spelling, right? Perihelion of Mercury, let's say, each planet. So the idea is that planets go in an ellipse, right? But when they come back, they do not come back to the same point. So they can switch a little bit. So you get off from where you started a little bit. And why does that happen? In Newtonian physics, according to Newton's law of gravitation, they should come back to the same point. That's the expectation, that they should come back to the same point, but often they do not. And then you say that, oh, that's because there is Jupiter there. That's a heavy object there. So it tries to pull it to a certain extent, and it's no more the equations that we started with. And you could predict to a certain extent, except eventually it was realized that even if you take care of everything around, it was not possible to explain the perihelion of Mercury. In fact, it reached a stage where it was predicted that there is another planet inside Mercury. Like we know that there is Mercury, Venus, Earth, and so on. But by 1850s or probably 1880s, they were very clear that Mercury's perihelion cannot be explained by anything that you see in the sky. Okay, and they were so sure about their equations and derivations that there has to be something, right? And they said that no, Newton has to be correct. So they predicted that there is a planet inside Mercury. It's just that we don't see it. Sun is so bright, so it's never visible to us. But there must be a planet, and they predicted its mass also, so that it explains Mercury. It's just that it turned out that there is apparently there is no such planet. We don't know for sure, but it can be explained using what turned out to be Einstein's special theory of relativity. So that's how it got explained. But it is remarkable that they were so confident that they could predict a planet as such. And in fact, in the same context, I should say, Pluto was predicted in the same manner. Like Pluto was not seen first, it was predicted. They knew that there has to be a planet having this orbit because they could see the effect of those planets on other planets. So it's remarkable that how accurate they could be, that they could predict such planets before. So that we will do that, and we will try to get a very like at a perturbative level, a simple idea of perihelion of Mercury. So I think that will be nice. And since I pointed out Einstein's relativity, we will also do special theory of relativity at the end. So it has to come at a price. So we will see how much we can cover. When I am teaching electromagnetism, I do cover special relativity there also. So when both the courses are in my control, I try to sometimes compromise special relativity here and try to get it done there. But this is one of those topics where I've noticed that every course tries to say that you've seen it somewhere else. And it's very likely that you never see it at all. This course says that you will see it there, that course will say that you will see it here, and you never see it at all. How many of you have seen special relativity at reasonable rigor, with a reasonable rigor, not just the idea of length contraction and time dilation, with a little rigor in the sense that you have seen the Newton's equation or acceleration, idea of acceleration in relativity. So have you guys seen that? Aryan and Abdullah?
Not much, just the idea. Sorry.
Just the idea. So you never saw it in a complete form in a course. Okay. So that's what happens. I think that's very standard that in the undergraduate level, you'll say, you will see it in master's level, and in master's level, you say that, oh, you must have seen this in the undergraduate level. So we'll try to, so I'll try to do this, but this is a good handful of this, and we will see how much we can do. I should point out to Aryan and Abdullah that I think others already know about this. I have all the material that I can post online. I have it available on the website. If you like, we had a website before. If you remove the later part, the TC and the numbers, that's the main website I maintain. It is my personal website. And there is a link for that. It says past courses. If you're right there on the website, it should say past courses. And there are all the courses that I have taught. Often there is not much in it, but in the last few semesters, there are recordings of all the lectures. In fact, all the lectures and homework, whatever we could have from last spring, is available there. So that's a useful resource you can use. You can come if you have the time, then you can listen to something before and then again listen to it here. And if you go back in 2013, I think it was 2013 or no, probably 2015 or so, I have taught, first time when I taught classical mechanics, probably I have put in the notes, handwritten notes might be available. I'm not sure if classical mechanics has it or not. At least first time when I taught here, I used to maintain all the handwritten notes, but I'm not sure if classical mechanics has it. So that's a resource you can use. Not necessary that you need to use it, but if you want, you should go for it. Often there are solutions available in that form. Sometimes I post solutions of a homework, not always. Then it's possible to find it in my own website. That's all perfectly fine. There's nothing wrong in looking into solutions. Again, most of the problems I give probably have solutions on the internet. So it's okay to use those things, but do try on your own first. I'm just trying to tell you, especially to Aryan and Abdullah, that if you're not aware, you should be aware that there is such a resource. Okay. Anything else you guys want to add to that? What you guys find useful? Rob, Michael, and Luke, you have something to tell about the past courses to Aryan and Abdullah? Even if it is not useful, you should tell them that, yeah, it is not useful. Okay, they don't have anything specific to say, or it might also mean that they might want to tell you separately, not in front of me. So do talk to them. So these things are useful. I believe they're useful. Do talk to them. Okay, so let's do a little bit. What's the time? Let's see. Oh, I don't have a clock here. Let's see. Exit full screen.
10:30.
Yeah, 10:30. Okay, I have 20 minutes. And it is, the writings were visible, right? Whatever I was writing here. So the only difference I had was that I closed the window instead of opening the window. So I want, the light is less today, but probably the contrast comes out better that way. Okay, so let's start with Newton's laws. Laws of motion, let's say. There are three laws. So the second law is says that mass times acceleration is equal to, so we are talking about the mass, so something has a mass, that's the idea, and we are interested in the motion. So often you say acceleration is basically, sometimes you can say this is a motion, right? Motion is described by the acceleration. And Newton realized that you can actually determine the acceleration in terms of what he defined as forces. So it has to be the sum of forces. There could be many forces acting on this mass. So you add them all vectorially. So it's a vector equation. So add all the forces, and it turns out that you can determine the acceleration using that. That's the content of this equation, and I write it in this form. And since many of us use many of these textbooks everywhere uses similar notations, the idea is that these are forces and there are so many of them. So hopefully it's clear what I have written. But if you were to really ask questions, you should, how it goes about is that first thing you would do is that you have to define your time. So you say that it's a time t, and let's say time t, and there is position, which is, let's say, given by a vector, right? It's a three-dimensional space, and it's so these are the two things that come about. Right in the beginning, if you were to really ask yourself what is like, one has to really have a clear picture of what time is and what position is, and most often it is not easy to define these things from the scratch. Right? If I were to ask how do you define time, it can be hard. In fact, the coordinate geometry for position that we have in our mind, the moment you say what is position, you have a rectangular coordinate system, x, y, and z, and we have a vector. All that is very recent. It's only in the last 500 years or so. Right? Before that, there was no coordinate geometry, and everything was written in terms of just geometry, I would say. Like you only knew triangles and circles and so on. You never wrote x, comma, y, comma, z. The rectangular coordinate system did not exist. And so that could be hard, but so, and I don't think we ever try to define it, make it concrete, but the expectation that we have the idea of time, and there is the idea of position already in some form with us. Right? Is that correct? Am I saying it right? Do you guys have a better way of defining position and time? Any difference between position and time? What's the difference you can think of between position and time? There is one significant difference, and that is that the change in time is always greater than zero. Like for example, let's say let's think of it as one dimension. Let's say this is x, right? So I have 0 here, 1 here, 2 here, and I have -1 here, -2 here. So you can think of, especially if you're saying that this is the position of an object, I can first go to 2 and then come back to -1. Right? Position can be, it can oscillate, right? But when it comes to time, it's the same idea you have some numbers that determine that, right? That is a linear concept in time, that 0, 1, 2, 3, what are the values time can take. But once you start with 0 and then go to 1, it has to keep going in that direction. You cannot come back, right? To our knowledge, we cannot change time to our convenience, right? It's monotonic. The best you can say is that time is monotonic. And then you say that, okay, let's take a linear idea for time, but that's not really necessary. But time is surely monotonic. It goes in the direction, in one direction all the time. It doesn't come back. What's the consequence of that? There is a physical principle associated with that.
We can't go in past.
Causality.
Correct. Causality is causality that? No, causality is something more than what I'm saying. right? I'm only saying that we keep increasing in time. Causality has to do with the idea that something from the future doesn't come in the past or doesn't affect the past, right? Maybe it is related. Yeah, maybe it is related. I don't want to insist that. But what I had in mind was entropy. So there is this principle of entropy, which always increases. For example, a cold object, if energy is not a consideration at all, if you do not have energy as a constraint, then entropy is always increasing. That's directly related to the idea that time is having a direction, in the sense that it's always monotonic. And causality, I believe, is an independent principle. That's my understanding. That's a good question for quiz, right? So we should have a feel for what quiz is about. So the quiz is going to be that, is there a connection between causality and the direction of time? It would mean that, is there a direct relation between entropy and causality? Okay, is that clear? Don't expect to have a concrete answer. It's just an exploratory question. And usually the quizzes are due the next lecture, but next lecture we don't meet, right, in person, so it's hard for you to submit it. So for this week, the quiz will be due on Tuesday, presuming that there is going to be a in-class experience at that time. If not, then we will think about how to make this due. Okay, is that clear? So that gives a feel for quizzes also. Okay, so that's time and position, and there is this idea that time is a unidirectional. Once you define these things, the second is you can define velocity, right? Velocity is very concrete. Once you have position and time given to you, then we can define velocity. And in fact, this position is a function of time, right? Like it changes with time. So that's the whole idea, that this is the position of this mass m, and it changes with time. And velocity, you say, is change in position over change in time, right? And that leads to a problem immediately. And what's the problem? If you define velocity like this, what's the challenge you experience? Is there a challenge?
There's no instantaneous velocity.
Correct.
It's just
So the idea is that if you define it this way, time can be zero, right? If this is zero, as time change in time becomes really zero, change in position also becomes zero. This seems to suggest that there is a 0 over 0, which is an undefined object, right? So it is not well defined, at least when you make the time smaller and smaller. So for this purpose, that is why calculus was invented. You actually take the limit delta t tends to 0, and that's a well-defined idea, right? That's the idea of calculus. That's a basic point where calculus comes in, that this is given a well-defined meaning, and that is your velocity. Same thing, acceleration is limit delta t tends to 0 of change in velocity over change in time. Notice these two, even though first time when it was done, that was a big leap you made, but that's a well-defined idea, unlike time and position. Time and position is slightly, there is an intuitive feel for what we say. But the next step is even worse. You introduce mass, m, and then you introduce the idea of force, without at least in my understanding, you don't define these things very well. Like if you ask yourself, like velocity and acceleration are mathematically well-defined concepts. But mass and force, if I were to ask you what is force, I feel it is slightly vague, especially the normal force, right? You have to do a lot of explanation for that. Oh, there is a, if I'm pushing something, something moves, right? So there is an intuitive feel to the idea of force. We'll come to the certain forces have more concreteness to it, like laws of gravitational law. Newton's law of gravitation is very concrete, but many of the forces that we see, the normal force, force of friction, the tension force, has a less amount of concreteness in it, the way it is introduced at Newton's, in the context of Newton's law. Because with these, if you say a lot of dependence on intuition, the idea of Newton is that mass times acceleration, or let me this time write it slightly differently. Acceleration, like the main idea of Newton is that acceleration, the way he defined it here, is equal to the sum of forces divided by the mass m. And that clearly gives the idea that if you say this is motion, acceleration, forces help motion. If you want to make something move, you exert a force. And mass in this context, it is going against, I mean, it tries to resist motion. So this is often called inertia in this sense, that it tries to resist motion. And there are, one can extend this, and there is a lot of reasons why you would try to understand this idea of mass. But we will stick to this, and for us, Newton's law will be mass times acceleration is equal to the sum of the forces. And here in the first two lectures, so what I will do is that I will try to pick some forces and make it, try to do some simple exercises involving some simple kind of forces. So what are the forces that we will do? So let's see. So in the introductory level physics, what are the forces you would see is probably gravity. So let's say one is gravity. And usually it is uniform, so you say this mg, right? And then you have normal force. And then you have force of tension. These are the forces that you come across. And then there is force of friction, the contact friction, right? So this is contact friction. That's broadly what it is. Of course, you can list, this is a never ending list you can make, but most of these are empirical. What I will do here in one or two lectures is, let's talk about a class of forces. Let's say first one could be uniform. So it's a uniform is constant force, let's say, instead of saying uniform, it's a constant force. By constant, I mean constant in position. So let's just say constant in everything, a constant force. That's what we study in introductory level physics a lot. That's what happens if you're on the surface of Earth and you drop something. For a good approximation, it is constant. Second is, I won't do this too much in detail, so it has only time dependence. So let's think of a force, hypothetical force. It depends only on time, right? So only time dependence in that. Next is, we say it is not having any time dependence, but having only position dependence. And this has been the most successful part in Newton's laws, and that's because Newton's law of gravitation is such an example where it depends only on position. Right? Newton's law of gravitation depends on m1, m2, which is pretty much constant. It doesn't change over r squared. It not only depends on position, it depends on the magnitude of the relative distance between two masses. Right? So we will try to just go over a couple of examples in that. And the next is we can talk about forces that depend only on velocity. What is an example of a force that depends only on velocity?
Drag.
Drag, that's good, very good. That's a drag force. Good. Any other force?
I think air resistance force.
Air resistance, I think that's what Michael means by drag. Like drag is when you're dropping something in air, there is a velocity. If you're going really fast, for example, a ski, or what is that? What's that called when you drop yourself from the sky? What's that sport called?
Skydiving.
Yes, skydiving, right? So skydiving is where the air resistance comes in, and that is broadly called drag. So I think, Aryan, you're meaning the same thing as Michael. So any other force you can think of where velocity is there? That is a very common force that you come across.
Also, friction depends on velocity.
Yes, all that is drag, right? These are all like, it can be linear in velocity, square in velocity. Mostly that's what we mean by drag. So dissipation, if you want, most of the dissipation depends on velocity. So I think friction, drag, air resistance, all those are, I think, different terminologies for the same idea, I think. But there is one more very common force that you come across and much more rigorous than drag, a lot more rigorous.
The magnetic force.
Correct. The magnetic force is a velocity dependent quantity, right? So it's called the Lorentz force. In a magnetic field, if you have a charge, there is a velocity dependence to that. It's a reasonably rich idea in the sense its direction is not in the direction of the, or its acceleration, how do you say this? Yeah, if you exert a magnetic field, the force is not in the direction of the magnetic field, not in the direction of magnetic field, not in the direction of velocity. Instead, it's in the third direction that's given by a cross product. So it is kind of, you can say, less intuitive, but you see it so often that after you study it, it's intuitive. But in the beginning, you can say that it's not very intuitive. So we'll try to do some examples on each one of them in the next lecture, or at the most 2 lectures, and then immediately switch over to what we want to do, least action principle, and try to do calculus of variations there. Okay, and that makes it .1050 on my computer here. Yes, 1050, and let's stop here. Any general comments or questions you have? If not, yeah, welcome again, Aryan and Abdullah. You talk to others as much as you can online. Feel free to talk.
Thank you very much.
Contact me. Yeah. Yeah. Great, Abdullah. Okay, enjoy, guys. And the recording will be available on the website, okay, of today. Yeah.
Thanks.
Okay.
Have a good
Thank you.
day.
You too.
See ya.
Bye.
Bye, everyone.
Bye.
Thank you, Professor.
Thank you, Aryan. Yeah.